Hello, my name is Michael Steil, and our presentation will be in two parts. The first part is about the old Xbox hacking, the second one will be about Xbox 360 hacking, so as much as we already have, because the Xbox has just been released 3 weeks ago, so there's not so much known. I can say that now, Linux doesn't run on it yet. But we have quite some information on that, and that part will be done by Felix Domke after my first part. So that you know what you can expect from my first part. We have had previous talks about Xbox done in 2002, in 2003, and in August of 2005 I did some additional research, and including information from the Bunny book, and all this together makes today's presentation. So I must warn you that there is few really new stuff. All of what I'm going to tell you has been done until 2003, but there are many things that haven't been previously released because we wanted to have an additional way if Microsoft updates the Xbox, so we didn't disclose that information. And well, another point is that what has been done in the last year is real reverse engineering of how Microsoft did the Xbox security system. So this talk is more like a conclusion or a summary of the complete system. And I must also tell that most of what has been done, most of the Xbox hacking has been done by other great people, has not been done by me. So let's look at the title, What Can You Expect? We are talking about security, we are talking about hardware security. Don't mistake this as security, what to do against buffer exploits. That's not this kind of security, it's more like a hardware vendor lock-in security. And yes, I admit that the title is quite catchy about the 17 mistakes that Microsoft made. Now, well, I even have to emphasize that it's not 17 individual mistakes, but it is 17 classes of mistakes. Several mistakes have been made more than once. So the question is it really Microsoft? Are they to blame that they made all these mistakes? That's a theory of Bruce Schneier, who commented on a previous article I wrote, and his comment was lots of kindergarten security mistakes. Now, the question is, was he right? Is it really that simple? And that's why I'm going to start presenting everything from Microsoft's view. We will try to construct the security system, and afterwards we will hack it. So, if the mistakes are obvious, then Schneier was right, and yeah, kindergarten security mistakes. And if the mistakes are not at all obvious, then we have proven that it's just not easy doing a security system. So what I expect from you now is that you pretend to be Microsoft and think like Microsoft. Let's look back at the year 2000. Home entertainment. Microsoft competes mainly in home entertainment against Sony. Sony has lots of products already on the market. It's there with the Discman, with the mini disc. Microsoft is also there in some way with Windows Media Audio, and also NVIDIA with Windows Media Technologies. But Sony has the PlayStation, and Microsoft doesn't really have a complete product in the living room, and so they wanted their own video gaming console. So I told you that was in 2000, and the PlayStation 2 was going to be out a year and a half after that, and Microsoft badly needed an Xbox, their video game console, within 2 years. And there is not really a way to construct a complete new gaming console plus a security system, and giving the developers the time to develop their games within 2 years. So what they did was basically use PC hardware, use Windows software, use DirectX libs, and put it in a smaller case. So this method was fast. They could do this in 2 years, and it was also cheap because they could use off-the-shelf components. For example, the Celeron. The Celeron is a standard Celeron 3 mobile with 733 megahertz. All the other stuff, it's NVIDIA GeForce hardware. Not at all that custom. It's a standard 10 gigabytes hard disk. They could use DVD-ROM technology. They had USB ports for the controllers. It's everything quite standard and quite easy to develop and to maintain. And it has the Windows 2000 kernel a bit stripped down so that it fits into less memory. So the Xbox actually is just a PC. But the question is, well, what is a PC? What is a PC? What is a Mac? Why is one computer a PC? Why might it not be a PC? If a computer has an x86 CPU, is it already a PC? If it has a VGA style GPU, is it a PC then? Does it need all the PCI, AGP, IDE, USB, all these technologies? Is it already a PC then? Maybe not, but what the Xbox does have is all the legacy stuff. That is the old 1982 interrupt controller. Nobody uses that anymore today. Or the old timer. I think it will be used, but it's 1982 stuff. And it also has the A20 gate, all the old legacy components. So if it is a PC, it would be trivial to run Linux or anything on it, but well, we need a security system for that, not just against Linux, but let's look at the different threats. We have Linux as one possible threat, so that people would use it as a computer, which is a bad thing because the Xbox is sold at loss and they make money with the games. So if someone uses it as a PC, they might really lose money, so they didn't want that. And also it's a prestige question. Homebrew software is also no good because if someone makes a media player or a browser, a media player that is not Microsoft Media Player or a browser that is not Internet Explorer, it would also be a bad thing because they do want the monopoly on that platform, which is always a good thing. Copy games is pretty obvious, they want to prevent that. And unlicensed games, that's something that some people might remember from Sega versus Accolade, that game developers have to pay royalties to Microsoft for every game, and if anyone could make games and unlicensed games were possible that Microsoft did not authorize, they would not gain that money. These 4 security threats can be addressed with a single system. The idea of this system is to make only authentic code run. Every time execution is passed from one chunk of code to the next chunk of code, all you have to do is check for the integrity of this. And this is called the chain of trust. A chain of trust that reminds us of what? Chain of trust and everything, all that is exactly the trusted computing stuff that everyone is afraid of. The Xbox has a complete trusted computing implementation in it. So in a chain of trust, where does execution get passed to another chunk of code? When the system starts up, we must load a Windows operating system or something, and we have to check whether this Windows is okay, whether someone has tampered with that. Also, if Windows loads a game or any other application, then another check has to be made. And let's look at what PCs look like. Well, actually, that's an Xbox, but it's just like a PC. We have a CPU there. We have the graphics processor there, which is integrated into the North Bridge, as with the Enforce chipset, Enforce 1 chipset that NVIDIA sold for the PC as well. We have a South Bridge there. We have his memory, and there's a flash chip. So what does a PC do if you turn it on? Where does it start its execution? Let's look at this. This is the memory map of a PC. At the very bottom, you have RAM. And at the top, you have the flash mapped into the addressing space. Now the CPU starts at this address. That's at the very top, minus 16 bytes. And this must be covered by flash on a PC. It would typically be code like this, like switch into protected mode, do anything. But what if we modified that somehow? Then we could just run our code. Well, not our code, we are Microsoft. The attackers could run their code. So, how could they make their code to be in there in this flash ROM? Well, it's pretty obvious. The first possibility is you can just replace the flash chip. If you can put a socket in, and you can put your own flash chip in there, and it would run from would run your code there, which would be a pretty bad idea. The second thing is you can override the flash chip. There is a connector where you can attach your own flash chip. Now, why is that? Why did they add this extra connector? And the reason is money, because it is quite expensive if you put ROM inside a computer. It is also expensive if you use a flash chip, which you pre-program and then put into the mainboard, but it's a lot cheaper to put an empty ROM chip in it. Then the chipset must support it, that if the ROM chip is empty, then it will boot off an external ROM chip. And this ROM chip can then download over the network the image and flash it on the system to make all this a lot cheaper. So Microsoft did need this connector for an override ROM. And the third thing is it is a flash chip, so you can also overwrite it in a way. So that is not what we want. That must not be the case. There are 3 of these attacks. What possibilities do we have? The first possibility would be to use a ROM chip instead of a flash chip. A ROM chip has the features that it is more expensive. It cannot be overwritten. It cannot be overridden because we don't need that in-system flashing. But the problem is we can still replace it. We could put a socket in it, and we would have lost. The second possibility is we could integrate the ROM chip into some other device. We wouldn't use any external chip, but we could integrate the ROM into the CPU. Then there would be no way to overwrite it because it is ROM, no way to override it, and there would be no way to replace it because you would have to replace the CPU, which just doesn't make sense because you would pay for the CPU twice and you would have to do soldering. Nobody would do that. It is very effective, but it's very expensive to use a custom CPU for that. Well, Microsoft wanted to have a cheap console, and they wanted to use off-the-shelf components, and they used the Celeron, and they couldn't have used off-the-shelf Celerons if the ROM wasn't there. So there is a third possibility. That is, it has been done before. I think the Nintendo 64 has done that, and I think also the Nintendo Game Boy. They integrate a small ROM, a really small ROM, just a few hundred bytes, into some device, into some chip that cannot be replaced, and then use a standard external flash chip. What must be done there is, well, this is obviously cheap, because you have a small ROM. A small ROM is always better than a big ROM. And, well, the question is where to put it. I'll come to that later. And it is effective. It is effective because the idea is that this secret ROM, it's 512 bytes on the Xbox, is at the very top of memory. If the CPU starts, it will not start from external flash memories, but it will start from this secret ROM that is embedded into some chip. This secret ROM can now verify the flash integrity, and if okay, it will pass execution to flash. The question is now where we would put it. I told you that putting it into the CPU is not a good idea because it is too expensive, but the South Bridge is really great because the South Bridge is a custom chip anyway. And well, the downside of this is that while it is a secret ROM, it should be hidden so that people are less likely to attack it successfully. But data will travel over a bus if it is in the CPU. No data will travel over a bus. There should be no way to sniff it, or at least easily. This way, it can be sniffed, but it's not really easy. It's a double data rate, 200 megahertz bus, and few people have the equipment to sniff this bus. Well, but we have a problem now with flash verification. I told you we must verify that the kernel in this external flash memory that is untrusted is authentic and nothing has been changed. So our secret ROM must make sure that it is okay, which could be done, for example, with an RSA-based signature. That's a great idea, and this is probably very effective, but we will never get RSA in, say, 512 bytes. If we need 5 kilobytes, that's really a lot more expensive. So, but there are alternatives. The alternative, well, one alternative would be not to use a signature, but to use a hash. That is to use a checksum over the complete flash. The problem of the checksum is that there's no way to update the Windows kernel in flash ROM on later revisions of the Xbox without also updating the Southbridge chips. Because any new revision would not be accepted because the checksum is of course different. But what we can do is we can introduce another link in our chain of trust which will hash, well, the secret ROM will just hash a second bootloader, 2BL. And the second bootloader can be of any size. And this second bootloader, which is in flash and which is hashed and must be authentic then, can then use RSA to check the integrity of the kernel. So this looks pretty secure. We cannot change 2BL anymore, but we don't need to. But we can update the kernel. Now, what does our secret ROM have to do? I told you it has to verify the integrity of the second bootloader, 2BL, with a hash. It has to pass control to the 2BL if everything is okay. But it also has to decrypt 2BL. And 2BL will, in turn, also decrypt the kernel. Because the whole flash, it would be a good idea if the whole flash was encrypted. So it makes attackers, it makes it a lot harder for attackers to see any code and to find any vulnerabilities if they don't see the code. So we should really have it encrypted in the chip. But in order to decrypt it, well, where would we store it? We would have to store it in RAM. And RAM is definitely not stable at this point if you turn on the Xbox and after 20 cycles or so, RAM is certainly not stable for one simple reason. Microsoft bought RAM chips by Samsung and they took all RAM chips that Samsung could deliver, not just the good ones, also the faulty ones. The faulty ones is these that don't do the 200 megahertz, but they're only stable at 180. So some Xboxes run with a memory at a slower clock frequency than others. So we really do have to make a stress test at the beginning to check how good the RAM is, perhaps depending on the temperature, and only after that we can really do something with RAM. But the question is, will all this, including the memory stress test, fit in something like 512 bytes? And that's obviously not possible. But we can put some of the code that has to be executed outside of these 512 bytes. We could, of course, have a large chunk of code in flash memory and just call it and make the memory initialization, jump back into the secret code and do all the crypto stuff. But this would be against all the security features because anyone can change the flash ROM. So we must not execute anything from flash ROM as long as it is not verified. The idea is to use a virtual machine which can do computer initialization. That virtual machine looks about like that on the right. It's a big while loop which can interpret several commands that can do all this. It can read and write from memory, which it needs for memory initialization. It can access ports, I/O ports, that is. It can do PCI config cycles, that is clock RAM down, and it can do some calculations and if-then and loops. This language has been called by hackers lately the xcodes, and it's a really neat way to move code out of these 512 bytes into flash ROM without compromising security. So our memory initialization in xcode language would look like this. We have that poke PCI that sets memory frequency to 200 megahertz. Then we would store something in memory, read it back, check whether it is okay. If okay, go to end. If not, try it again with 195. That's exactly how these xcodes would work. But that's additional complexity for the whole system. So we should really have some thoughts about what people could do with that virtual machine. What if that secret ROM that we put into the Southbridge gets eventually revealed? Then people understand how to write these xcodes themselves. So we must really make sure, because the Xbox are not verified for integrity, we can't just do all that in 512 bytes of code. We must make sure that nobody does anything nasty with the xcodes. And there are several attacks that should be quite obvious. The first one is we could dump the secret ROM. So if someone has some clue how the xcodes already work. The xcodes can be used to read all that, the secret ROM, which is mapped into memory at the very top, at the top of 512 bytes, and put it out at a very slow port, like the I2C port, for example, and sniff it there. So that's a quite effective attack to read the 512 bytes, which must not be revealed. And it is done by masking the high addresses. So every time you read from memory, or I think even write from memory, write to memory, the upper 4 bits will be cleared. So we can effectively only access the lower 256 megabyte of the address space, which is okay for memory initialization because we only have 64. So there is no way for the xcodes to access the secret ROM and dump it somewhere. A second attack would be to turn off the secret ROM. We have the secret ROM there lying over the flash. But what if the secret ROM gets turned off? Then the code that is just executing inside the secret ROM would fall down into flash. And that would be a quite bad thing. And that's exactly the statement that does this, because the chipset has the functionality to turn off the ROM for reasons I'm going to explain later. And we must make sure that xcodes can never disable the ROM, or else we would fall down into untrusted flash, which is a bit like this picture here. Because this code will turn it off, we will fall down, yeah. And we must check for this code. And this is done by this code here. Every time we do a poke PCI, we test whether it's really that single instruction. And if it is, then we clear that bit that would turn off the ROM. So that poke PCI will have no effect. Okay, let's talk about decryption and hashing. We must now, after memory initialization and all that virtual machine stuff, we must think about a way to decrypt and also checksum or hash the kernel that is stored in the untrusted external flash memory. And we need an effective, working, and really small algorithm. There are really small algorithms like those that have a secret key. This will be expanded to a seed. And this seed can generate a key stream. And this key stream, every single byte of this key stream will be XORed with the ciphertext we have in flash memory, and we get the plain text output. That's how RC4 and RC5, for example, do it. And there can be one additional property of these, that we have feedback of the data that gets decrypted into the seed. What happens then is that if, for example, we have a different ciphertext for one single byte, then the plain text will, of course, be changed. But because of the feedback, the whole key stream afterwards will also be different than before. And therefore, the whole plain text that comes out at the other side will also be different. So what this feedback gives us is that if you change a single byte, then the complete decryption will be altered. And even until the last few bytes, they all will also be different if you change a single byte. So what we get is we get a hash for free. All we have to check is whether the last few bytes are the same or have been changed. So that's a pretty neat way to combine decryption and hashing in a single algorithm if we have this feedback functionality. Now, what do we do if the flash is not correct? What if the flash check fails? We must panic in some way. We must blink the LED. We must not turn off the Xbox because the user wouldn't know what has happened if it really is a fault. We must blink the LEDs in some way to communicate. And obviously, we must hold the CPU, and we must also disable the secret ROM. That's why there is the functionality of disabling the secret ROM, because an attacker could just make that hash fail so that the Xbox deliberately panics. And while it panics and is turned on, someone could attach extra hardware to read that data, which is a lot easier than sniffing a bus. So secret ROM must be disabled. So how can we panic? That's a problem, because how would you crash a car while the motor is off? The problem is we could turn off the CPU and then turn off the secret ROM. But if we turn off the CPU, who can turn off the secret ROM? And on the other hand, if we turn off the secret ROM, then the CPU, where would the code be to turn off, to hold the CPU? So we have a real problem there. And Microsoft was very, very creative to solve this problem. That is, we drive just against the top of memory. That's the top of memory, that's the last few instructions that can fit there. And we just put these instructions that turn off the secret ROM at the very top of memory of our address space. So what does the CPU do if it goes against the very top of that? There's a barrier there. There will be a double fault, according to the data sheets, and the CPU will be halted. So we have both. We have turned it off and we have halted it because it ran against the end of memory. Okay, let's summarize the security system. What we do, we have that secret ROM, which is inside the south bridge. It is hard to sniff and is not possible to replace it. It is not possible to override or overwrite that secret ROM at least. And it's very hard to dump. It first must initialize RAM with this xcode technology, which is stored in flash, but which is secured. We have looked at all the cases that are possible attacks. And it must decrypt and hash the 2BL and panic if something goes wrong. Okay, now put off your standard glasses and put on your sunglasses. We are now the hackers. Okay, now we have an Xbox and we know nothing about it. And there is someone, Bunny, who first, of course, dumped the flash ROM. Put it online, got a call from Microsoft's lawyers and put it offline again. Okay, Bunny looked, of course, at that ROM and looked where the x86 would start, at that very top address, -16. The question is now, what did he see? What was there at the upper 512 bytes of his flash ROM? What should there be? Zeros? Interestingly, no. What Bunny saw was the upper 212 bytes of flash contain a virtual machine that can do many interesting things. It has decryption and hash code, RC5. It has panic code. But still, if he changed it, nothing happened. Of course, he found out that this was not the real thing that he was editing. These 412 bytes had no effect whatsoever because there was some secret ROM. And this code didn't work. The key was wrong. Something was wrong there. It looked quite okay, but it didn't do anything. Well, Bunny, it was obvious for Bunny that the CPU didn't boot off this flash, although there was code there, and there had to be a secret ROM somewhere. So he sniffed the hypertransport bus and eventually had the 512 bytes of secret code. And in this secret code he saw there also was a virtual machine, RC4 decryption and hash code, panic code. Well, but the 2BL is hashed. Now what can we do? Let's look at how this RC5 algorithm that we spoke about earlier looks like. We have the secret key, the seed, and it makes that key stream, which will, if you change a single byte, will change the complete key stream. If we have that feedback. RC5 has that feedback. RC4 does not. And the secret ROM uses RC4. So if a single byte gets changed, then only that byte gets changed in the plain text. But the key stream does not get changed, and the last few bytes also are the same. So effectively, you can't use RC4 as a hash. So there was no hash. They had some code which would do the decryption, which worked, and which looked like it would do a hash, but it didn't. We also had the RC4 secret key, which was, of course, in ROM. So we could decrypt 2BL and the kernel and everything with the secret key. And there was no hash. So all we had to do is just re-encrypt our data with that RC4 key and put it where the second bootloader would be. So it was quite trivial then for mod chips of the first generation just to disable the onboard RAM and add a parallel ROM to the complete system, which would have a modified ROM in it which would allow copied games, or a modified ROM which would run Linux or something. Second generation mod chips even managed to do everything in 9 wires because I told you about the method that there is an LPC override. If the flash chip is missing, then it can boot off an external flash chip that is connected just with 9 wires, very easy to solder. All you have to do is ground a single data line and will boot off the external LPC ROM, and you'll have to just solder it there. So Microsoft had basically lost at that point. But there was also a problem with the Xbox Linux bootloader because when we did our own ROM that would eventually run Linux, we couldn't just ship that secret RC4 key with our build scripts. That just didn't feel right. So we had to find a better way and just look at the ROM code again and see perhaps there might be some more problems. Let's look at that crash thing to halt the CPU. Now the question is this really true? Does it double fault at that point? Because the point is that memory is indeed a circle. Well, memory is a donut. So memory, after the end of memory, memory starts again. So does execution, if it passes over that border of FF to 0, is it really an exception? Does the CPU panic? Or perhaps it just continues executing at 0, and at 0 there's RAM. Someone named Weiser thought that perhaps the execution might be rolled over, so he put his own code there and let the second bootloader check fail deliberately so that the panic code would be executed. The question is now, how can we put some data to RAM? RAM, we can put something in flash code, but we can't put anything in RAM. So the solution is we use xcodes. Xcodes can store data in RAM. We just poke 2 instructions, that is a jump into flash memory, into the beginning of flash memory. We put that at 0 of RAM. Let the hash fail, and then it wraps around and jumps to the beginning of the flash, into our code, which flash is untrusted. We can just put our code there. And the point is, this really works. There's no exception, no double fault, nothing. But why? Well, we need a small history lesson. It's all these legacy components why this works. The 8086 CPU, that old ancient 1978 CPU, started at the very top of its address space minus 16 bytes. But there are also, you can always start either at the very end or at the very beginning of the address space. Other chips started at 0. So in order to make the Intel series compatible with memory layouts where we start either at the top or at the bottom, which was obviously important for Intel, they implemented an interesting hack. Unconnected addresses on any computer should always read back as FF. On an x86, FF behaves always like a knob. You know where this is going at? So if there is no ROM up there, there's always FF, and it knobs its way through these 16 instructions and starts again at 0, where people can put their ROM. So this is by design. Execution can start at 0, and internally this will be done by a wraparound, by executing around that wraparound. And well, all the CPUs today that Intel makes still do all this. But why did Microsoft do it wrong? This is very well documented in Intel datasheets. And that's also a question of history. Microsoft made this mistake because AMD CPUs don't have this behavior. AMD thought that this was a security risk. Hey. Okay. That this was a real security risk because there is a border there. There are segments and there are borders where you may not cross. So AMD did not implement this, and it wasn't needed anyway. So wer ist denn das? Okay. Wie geht das aus? So. So AMD CPUs are specified to halt at that point. And why? Well, did Microsoft just read the wrong data sheets? Microsoft used AMD CPUs in all prototypes. But why did they do that? Were they just stupid? No, they were not. Because the original deal was that AMD would do the chipset and the CPU, and that NVIDIA would do the graphics hardware. And in the last minute, Intel came in and said, well, let us do the CPU. But it wasn't that easy because the whole chipset was already the AMD chipset. It had hyper-transport, it had not RAM bus, but DDR RAM. It was a real AMD system. So Intel were the ones that really changed the complete design so that it was compatible with an Intel CPU. And that is the very reason that the name AMD is not found anywhere in the Xbox, although there is a lot of AMD technology there. The mainboard design, the South Bridge and the North Bridge, are completely AMD technology and just licensed by NVIDIA. And so are all the Enforce chipsets and their successors. Well, that was that last minute switch. Okay, that is one attack. That was one attack, but Microsoft don't just make one mistake. Another mistake was, well, they actually knew about this vulnerability, that we can turn off the ROM and then fall down to flash. This here again. And we had this code. Let's look at this code more closely. It examines whether this is really this address. But let's have a look at the data sheet again. The data sheet of PCI config cycles is like this. We have the register function device bus. We might have one bit that must be 1, and we have several bits that are reserved. And what happens if we use this very same address, but change some of the reserved bits? The same happens. It works. If we put FF in there, then it won't be caught, but it does work. The next slide illustrates this, how it can be exploited. If the secret ROM gets disabled, I marked with the X at the point where it would disable itself because it would just execute that instruction. It would fall down into flash. So what we have to do is we must prepare flash, and we can access flash, and put knobs in there, and I jump to somewhere else at the very end. So that is our landing zone. And then if execution at some point turns off the secret ROM, it explodes and then gets caught by our knobs, and it's in our code. So this was how it was exploited. But these unreserved bits is not just the only possibility to exploit that idea of disabling the ROM. Another one is this one. These xcodes are equivalent with the POPE PCI, and these are not checked. So this also does the same thing. So they checked for a case, but actually they just gave us a hint where to attack. Now, okay, there have been some things found, and Microsoft must now react, because basically everything is now possible. Linux is possible, homebrew is possible, and piracy is possible because the security system does nothing at all, basically because of Visor. Most people used that Visor wraparound backdoor. Well, just after Bunny found out that RC4 is no hash, Microsoft also understood that, finally, and they reacted. The question is now, how does Microsoft react? How did Microsoft react to finding out that RC4 cannot be used as a hash? A, do a complete code audit over their only 512 security code bytes. C, wait for more attacks. Perhaps someone else finds something similar. B, fix the hash. Or D, do nothing. So what would be your guess? Did anyone say C? B is it? They did fix the hash, which might have looked like a good idea, but actually it was the worst idea. Doing nothing, which is the same as wait for more attacks, would have been a lot better, or a code audit. Well, what they did was they found out that RC4 was no hash, and they still thought that RC5 was no option. Well, the history behind this RC5 thing, these 512 bytes that were in the flash, which shouldn't have belonged there, because it should have been in the secret code, and which did nothing at all, were actually an old version of that secret code. And this old version used RC5 encryption, and RC5 can be used as a hash. And then they changed it, they improved it to use RC4 and blew it. And they didn't use, we don't really know why they didn't use RC5, why they changed it into RC4. But RC5 wasn't that perfectly specified or finished at that time, so or perhaps some patent problems. It was a really new algorithm, so they went back to RC4. And still RC5 was no option at that point for some reason, so they had to add another tiny hash. It had to be really tiny, because 512 bytes, you only have perhaps, I don't know, 50 bytes left for additional code. We need a tiny hash, and many encryption algorithms can be used as a hash. So we need a tiny encryption algorithm. What happens if we put T? I must admit, I have no proof that it really worked like this, but they did indeed use the tiny encryption algorithm. And they fixed the secret ROM. They kept the RC4 in and added the T hash, which was really tiny and fit in there. While they were at it, they could also update the RC4 key to make it, well, we had to sniff it again then to have the new ROM, but it was trivial to update it. And they traced thousands of Southbridge chips that had already been made by NVIDIA. NVIDIA blamed a loss in one quarter completely on Microsoft because of that write-off on Xbox MCPs by way of the IT hacker. So that was a really, really expensive step. But that step made no difference. Of course, extracting the new ROM isn't any harder than extracting the old one. We could just have asked money again to dump it, but other people, including two people that are sitting in the audience, worked on an easier way, a way that was a lot easier. Old legacy stuff. Well, not everyone might already know how it works, but A20Gate is a really cool thing on the x86 architecture. Let me tell you how it works. The whole line started with the 8080. That was in 1974 or something. It had 64 kilobytes of memory, 16-bit. The 8086 had to be compatible. It was not machine code compatible, but it was assembly code compatible. And so the memory model had to be effectively the same, and the register were only 16 bits, so there was no easy way to address more than 16 bits, that is 64 kilobytes. And what they did is they just made segments of 64 kilobyte each. They could just have made 16 segments. So they would have another register, which could hold a number between 0 and 15, but they chose to have a register that could hold any number between 0 and 65,535, so a 16-bit register. So these these segments could overlap in memory. You could have a 64 kilobyte segment at 0, but you could also have it at every 16 bytes in memory. If you wanted to have the effective address of some byte, you had to multiply the segment with 16 and add the offset. But there's a nice side effect of this thing. And this side effect is at the very top. At the very top, the last segment that really makes sense is this segment, which will address up to the last byte of memory. But what is if we use the next segment? Then this would go, well, there's no memory. But we know memory is a donut, so memory is, at that point, mirrored again, so we have 0 at that point. So if you address the uppermost bytes of this 64 kilobyte segment, you get exactly what's at 0 in memory, which is an odd effect. And there were some people that used that, some operating systems by Microsoft used that. So, well, if we have, yeah, okay, let's look at some numbers here. If we have the last segment there is, and we go 16 bytes up, we already are at 1 megabyte, and this is then 0. Or if we take the highest address possible, then we will effectively be almost 64 kilobytes above 1 megabyte, which is 64 kilobytes at the very bottom of RAM. And what if we now have a CPU that can do more than 1 megabyte? The 286 could do more than 1 megabyte, and these two addresses are then effective. And the 286 would be incompatible with MS-DOS. Intel didn't know that. IBM found that out, and IBM had to hack around that. The old CPUs had only 20 address lines, up to 19. The 286 has the 20th address line, and so can address more memory. And those won't wrap around and will be incompatible. IBM had to hack around and include an option to pull 820 always to 0. This looks like this. We have the 286 and RAM, and this is the address bus. And the keyboard controller happened to have a spare pin, and they connected that pin to the 20th address line. So at any point, they could pull that to 0 and emulate that behavior. So there are two possible states of this. If you open the 820 gate, then you're in the native mode of the 286 and can address more than 1 megabyte of memory. And this is also abused by MS-DOS as high memory in real mode. If you close it, you simulate the wraparound and are compatible with old software. And all addresses, every effective address that gets generated by the CPU will always be ended with this number. Well, of course, today's CPUs still have this, and well, today's PCs still have this, but even the CPUs have it because it's now a pin of the CPU. It's not so easy to fiddle around with the bus anymore. So the CPU, I think, since the 486 have this feature embedded into them, and of course also the Pentium 3 used in the Xbox. How do we use that 820 hack? We take an Xbox and connect the 820 gate to GND. Then all addresses that will ever be used in memory will be ended with this key. And then the CPU starts at what location? If it would start at this location, it would start here. Now, where in the memory map is that? Let us look at the memory map. At the very top, we have flash, and we would have the position where it starts normally. And we have the secret ROM. Of course, it starts in secret ROM, but if we start at the different address using the 820 hack, we start about here. What is here? Flash is mirrored over 16 megabytes. So all we had to do is just connect a single wire and put our code there. Of course, that's no good idea for a mod chip, but it wasn't needed anyway. But it's a great and easy way to dump the ROM. We just could put our code that dumped the ROM to a slow speed bus like I2C. That's how we got the new ROM. And then we looked at it and saw there was a T-hash. Well, T wasn't quite such a good idea because This means that each T key has 3 other equivalent keys. In particular, it is easy to construct collisions for T when used in a Davis-Meyer hashing mode. This has been written about 6 years before Microsoft used T, and by Bruce Schneier again and others. So T was effectively not effective. T did do a hash, but it could be circumvented if you toggle 2 bits at the same time at specific locations, and then you can always construct something. And it was possible to construct something and change some jump to just jump somewhere else, jump to our code. But it wasn't necessary, because we could also look at some other vulnerabilities, whether they were still there. We just looked at that missed vulnerability, which would turn off the secret ROM. The old Xbox, if you turned off the secret ROM, you would fall down into flash. But they fixed that. On the new one, if you turned off secret ROM, you would fall down into hell. There's nothing there. The CPU would crash. Every time you access an address there, the system halts. So that's a good and effective countermeasures for all these turn-off attacks. You can never fall down into flash, because flash below there will be no flash at that position. So that mistake was fixed. Interestingly, they fixed this independently of, they found this out independently of the hackers, because they fixed it earlier than the hackers found the vulnerability. But there was still the visor vulnerability, and it still works. For one reason, because Microsoft acted too quickly. If they had waited just 2 months or done an effective code audit, they would have found it out. But at that moment, when Bunny released that ROM, that secret ROM, and everyone found out that the hash didn't work, Microsoft immediately put out new versions and trashed the old ones. So they didn't see that people also had other attacks. So there was no need to attack T, because Visor was still there, and it worked on both the old and the new Xboxes. So we didn't need 2 different ROMs. So what is the state today? Microsoft never trashed Southbridge chips again. I think it was just too expensive for them, or well, they had some problems with NVIDIA, probably. Maybe that's the reason why the Xbox 360 doesn't have NVIDIA chips, but ATI chips. Let's hope ATI knew of what Microsoft did with NVIDIA back then, and that losses in Q4 2002. Still in the latest revision of the Xbox, we have finally a real ROM chip. That ROM chip cannot be replaced because it is integrated into the video encoder, and it is real ROM. It cannot be overwritten, but the override functionality is still there, because the Southbridge controls the override. So we can still attach a mod chip to the LPC bus, 9-wire soldering, or even just put it in there, and all mod chips still work. So they have changed a lot of things, but basically nothing was effective, because well, they didn't want to lose any more money here. Okay, that was the hardware attacks. Now let's take a quick look at where else we can attack. We have this chain of trust, and the first check was really well hacked. The second check, when Windows starts a game, well, that Windows-like kernel that is in there starts a game, then there will be an RSA 2048-bit verification. Some people try to brute force that. I think they are still calculating. And this looked quite well, because it was basically taken from Windows code, and it was old and working code, not newly created 512 bytes. But there's another point that we can attack. If games load data, there are no checks. There are not necessarily checks, and most times there are none. So we can try just standard buffer exploit methods to not open it, to not change anything on the Xbox, but just get our code on it somehow. Let's look at the game, how we can exploit vulnerabilities in games. We must look at what data gets loaded by games. That's graphics, audio, video, everything from that custom DVDs that they have. The problem is that we cannot create original DVDs. They won't be accepted. It won't accept DVD-Rs, and there's no known way or no really easy way to really clone these original DVDs. So the only thing is save games. Save games are not stored on the DVD, they are stored either on the hard disk or on USB storage. Every memory card you use on the Xbox is a standard USB stick. And so you can plug it into a Linux computer or just use a USB stick with an adapter, put it into the Xbox, and if the correct image is there, then you have save games. That's how the action replay works, for example. Let's look at save game exploits. David Lee from Switzerland tried the games alphabetically. What's the first game on the alphabet? Nothing with A, but with 0. 007. He tried 007 and it had a save game vulnerability. So everything that had to be done was, David did a lot more, but everything that a standard user would have to do then was have the game. DD, that is copy the image of the hacked save game to a USB stick and connect it to the Xbox, load that save game. Not only with 007, there are several more games. About every 1 in 4 games that we checked have some kind of vulnerability in save games handling. The NX bit hadn't been invented back then. And if we load the save game, this happens. But now some may ask how this can be possible. If I have some buffer exploit in, let's say, Internet Explorer on a Windows system, I'm not in kernel mode. I can't shut down the system. I have only the privileges of the user that is running. Aren't games on the Xbox also running in user mode? No, all games run in kernel mode. There might be, I haven't heard any good explanation on why. They really modified Windows so that it had only a kernel mode. What is a possible explanation is that they don't switch context, they don't have TLB misses, which might be good for performance, but I doubt that it is really significant. Some other people say that it makes the environment, the programming environment easier, but it shouldn't really matter. But the problem remains. We have to run the game every time to boot Linux and go through that trailer and stuff and hello and select save game and everything. But perhaps we could look at some other application that crashed earlier perhaps. That's this nice application. This is the Xbox dashboard. The dashboard gets executed every time you turn on the Xbox and there's no DVD in the drive. With it you can manage your save games, you can play music from CDs or rip them into Windows Media format on the hard disk, can change the settings and everything. And this is stored on the hard disk. Some people might say that this Xbox dashboard code base is the single reason why the Xbox uses a hard disk and was the first gaming console to use a hard disk. Because perhaps you know a bit about the GameCube by Nintendo. The GameCube had about the same functionality in this menu. They could also save games, the settings, everything, all that. And Nintendo fit all that code in 2 megabytes, in a ROM chip of 2 megabytes. Microsoft fits this in 100 megabytes. ROM chips with 100 megabytes are expensive. So let's take a hard disk and find perhaps a way to make use of that hard disk. Perhaps they thought. That's all just ideas. By the way, the Xbox 360 doesn't come with a hard disk. You can have an optional hard disk, but it does work without hard disk, and it has 16 megabytes of flash. So they stripped it down to 16 megabytes. Not bad. The dashboard does a lot of things. Has data files on hard disk, of course. It loads audio files, 3D meshes for these nice 3D animations. It loads fonts, and it checksums audio, 3D meshes. It does not check some fonts, for whatever reason, and of course there's a vulnerability in the font handler. So If we abuse this in the correct way, we can change the dashboard into this. The process isn't all that complicated. The fonts make the system crash, make it use our code, run our code, which is embedded into the font files, and then we have full control of the machine, and we can reload the dashboard again, this time with the correct fonts, and while it is in memory, we can patch it. We can add this extra menu, and we can change the functionality that lies behind this extra menu to run some Linux bootloader from hard disk, and also to exchange the RSA key in case that we put in a Linux CD or we want to run Linux, so that we can use Linux signatures, Linux RSA signatures, instead of Microsoft's RSA signatures. So what the user had to do was just DD it to the USB stick as always, load the save game, and the save game had a script inside that installed the hacked fonts, because that script that was run in kernel mode from inside the save game had full control of the machine, could do anything on hard disk. We had a driver for the hard disk structures, so Linux could do that. And every time you turn on the Xbox, the fonts crash, and you get that hacked dashboard, which makes it possible to run Linux for a menu, or you can still run games. And it's interesting to note that this is a real chain of mistakes. Well, USB storage, using USB storage as memory cards made it a lot easier for the average person at home to duplicate this. But if any of the following hadn't existed, then there wouldn't have been the possibility. If games didn't run in kernel mode, there wouldn't have been this possibility. Or if there hadn't been any game exploits, if there was just good code, or if the fonts had been checksummed, or if there hadn't been a font exploit. And just this combination made it. And by the way, there's another exploit in the playlist handler. So there's lots of bugs in this code. And well, this code is trusted. After all, it's done by Microsoft. Microsoft fixed this. How did they fix it? Well, they could first really fix the bug. They did it right. They fixed that buffer vulnerability and shipped fixed versions of the dashboard with new Xboxes. And for all that, all those people who were on the Xbox Live online gaming network got updates without users' permissions. But hackers could just downgrade the dashboard again, put the hard disk into a PC or go into Linux and then DD the old image of an old Xbox or a backup of the image back there, and you still had the old dashboard with the old vulnerability. It still worked. So it wasn't really effective what Microsoft did. Okay, next step, Microsoft blacklists the old dashboard, of course. So the kernel has a blacklist so that it's not possible to run that old single executable with a certain checksum. But there was another executable on hard disk with the same bug. And of course they fixed it in this one as well when they recompiled. But the old dashboard also had this file and it wasn't blacklisted. So we could just use that file for the font exploit. Microsoft reacted. They blacklisted that extra file. Well, there was another file. That file was -update. The first Xbox is shipped without Xbox Live support. It was introduced about a year later. So every Xbox Live game had to have an update application for the dashboard so that the dashboard could do IP configuration, DSL configuration and all that. And this updater is in every Xbox Live game. It has the same bug. It is not blacklisted. And Microsoft did not blacklist this one for a single reason, because this old games must always work. If I buy a brand new Xbox, one of the latest series, and buy the old game of eBay, it must run. They cannot blacklist this. So effectively, the hackers have won at this point. And the situation today is that you can do all that mod chip stuff. That still works, as I told you before, but you can permanently mod an Xbox now to run anything and even still run games without opening it, even on the latest revisions of the Xbox. Now let's come to the 17 mistakes. There are 8 design mistakes, 6 implementation mistakes, and 3 policy mistakes. Perhaps you had a closer look at the summary of this talk as on the website, which said like 8 design mistakes, 5 implementation mistakes, and 3 policy mistakes, but still 17 mistakes. That was because originally my talk was about 60 mistakes, but then I submitted the paper and found 17 mistakes, and the other numbers hadn't been updated yet. So it's now 17 mistakes. And please note that these are mistake classes, and several of them had been made more than once. Let's start with design mistakes. Mistake number 1. Security versus money. There's no such thing as more secure or less secure. The only thing there is security is either effective or is not effective. There is never any sensible compromise between security and money. So if you think you don't want to spend so much money for security, there's a hard cut between secure and insecure. So if you go across that border, you will have an insecure system. So better spend that 1 cent more and you get a secure system. So trade-offs make no sense. And why do we do all this security stuff? Because we don't want to lose money on copies, on people just running Linux, all that. So we must spend money. That's the big thing. We can't save money on that. And they made this mistake several times. The in-system programming of Flash is the reason why there is no ROM chip but a Flash chip, and why there is that override functionality on all that. If they had taken a ROM chip from the beginning, then lots of these possibilities wouldn't have been there. Second thing is they used cheap and faulty RAM by Samsung, which was so much cheaper, but for that they needed that RAM initialization, and because of the RAM initialization, their code would not fit in 512 bytes, and therefore would have to use the virtual machine, and the virtual machine had the bugs. So, because of money again. Third thing is the secret ROM. They should have put it into the CPU, so it couldn't have been sniffed so easily, and bugs couldn't have been found so easily. But they put it into the South Bridge because it was cheaper than into the CPU. And they never updated the South Bridge again because it was so expensive the first time, and they thought they would get it right the second time. So that's basically the reason why the Xbox is still hardware vulnerable today. They could do that update, but they never did. The second thing is never do any trade-offs between security and speed, because speed doesn't really matter that much. It makes no sense for your applications or your hardware to be 10% faster, but then less secure. That might be effectively insecure, because 10% in computing is nothing. 200% faster or slower, that's a big thing, but 10% is not. And the fact that all games run in kernel mode might be because of speed. So that's yet another mistake. Mistake number 3, never underestimate the combination of weaknesses and what is possible with that. Be aware of that combination can lead to a successful attack, even if each vulnerability isn't that severe. And it makes no sense, if you have a component that is not perfectly secure, to put another barrier in front of it. Instead, you must really fix your vulnerable component. Where this has happened was with 007 and the dashboard. With 007 alone, we could run Linux. We could not eject the DVD tray because it would reset. We would have to buy that game, not rent it, buy it, because every time you reboot, you need it. It doesn't make so much, it's not so much fun. And the dashboard exploit alone wouldn't be so much fun, because you would have to connect that the hard disk to a PC and do all that. But in a combination, it is really trivial to do anything that you like. Mistake number 4, never underestimate the resources that hacker might have. Because many people have access to hardware at work. Many people have access to hardware at university. Or there are also commercial hackers, some people that just spend money, that invest money into finding security vulnerabilities. For the Xbox One, not much has been done there by commercial hackers, but I think this is getting more important in the future. And that point that this would be too expensive or too much work to hack is nonsense. Because there's never too much work. There are so many people out there, so many great people out there that can always make something that is hard can always break something like that. And Microsoft obviously underestimated that someone holding a PhD degree from the MIT and had access to MIT's hardware lab, that is Bunny, could quite easily sniff that hypertransport bus. Talking about making it easier or making it harder, it makes no sense to make something harder for hackers. Instead, you must make it impossible for hackers. If you just make it harder, this won't have any significant effect. Obstacles don't slow down hacking. Because there are so many hackers, it always works. It makes no sense to use your energy for that. You might even think that you're more secure by having so many obstacles, but you must have barriers instead. Use that resources to have real barriers that there is no practical way to cross or even no theoretic way to pass them. There are so many obstacles in the security system that had no real effect. The first one is that save games. Every save game is signed so that you can't just change a single byte. It won't be accepted then. But who signs the save games? The games, because they can be done at runtime. So every game has the private key for signing the save games. So just look at the games and you have the private key. So it made no difference at all. The hard disk is ATA password protected. If you put it in a PC, you can't read any sector. But if you turn on the PC and the Xbox and hot swap the cables, no problem. So the next point is that hiding the secret ROM also had effectively no effect because it was dumped, so there wouldn't really have been any necessity for that. And the last thing is that if you put a game into a PC drive, you can't read it. Well, if you could read it, it wouldn't be a problem because you can burn a copy, but the copy won't work. So this was just a small obstacle, but no barrier, and there was not really a sense in making that. A very important point is that, speaking of hacker groups, that you must never use a single security system to keep many different hackers off your system. Because all these hackers will then unite. And these groups might not have anything in common. Because the Linux guys were not interested in copies. The pirates were not interested in Linux. And the homebrew people were a very different group. But they did, in a way, either directly or indirectly by using each other's, what the others had in their own code. So in a way, they always work together. So instead, you must always find out who your enemies are and what they want, and then decide for every group of enemies on your security system. And for the Xbox, for example, there's the Linux homebrew and copies people. And what they should have done is, for example, like Sony did. Sony sold a Linux kit for the PlayStation 2. Therefore, all the Linux hackers, all the potential Linux hackers, had no interest in hacking the security system of the PS2. Why would they? Linux already ran on it, so it was quite easy. Only the homebrew and the copy people were left. That's 1/3 less people, or even a lot more less people. And Linux hackers tend to be quite good hackers, so that might be the reason why the Xbox has been hacked a lot more quickly than the PlayStation. So this possibility exists. Mistake number 7. So security by obscurity doesn't work. It might be quite obvious, but there are so many cases where they made something obscure and it didn't work. But what does work is the SHA-1 and the RSA. They use that heavily throughout the system. And at all cases where they use that old, well-proven code, there are no vulnerabilities that we could find. Well, they work if they are used correctly, of course. So don't use RC4 as a hash. So they hit the ROM, they encrypted the flash contents, which had no real effect. They hit the DVD contents, they hit the hard disk contents. Mistake number 8. Never release a quick fix. because a quick fix may be severely flawed and have no effect at all, or even be worse than the old version. And there is also the possibility that more holes get found afterwards, and you don't want to trash the chips again. So instead, audit the complete security system, because you have new knowledge how people hacked it. So think about that, what people have achieved, and think about similar attacks there, and look at your security system if there's anything similar there. And also look closely at what hackers are doing at the moment, and if there's something that they're doing, perhaps wait some time and wait for the next exploit. They made that mistake with the secret ROM hash function. They just replaced it, and they made that mistake with the dashboard font bug Odyssey in 7 steps. Let's look at implementation mistakes. Read data sheets. Many of these mistakes, many of these hints are quite trivial, but they have been made, these mistakes. You shouldn't hack around. Well, you must try out your stuff, but you really should have backup in the data sheets. And you shouldn't assume anything, especially if you replace some components. And especially if you use components with legacy functionality, you must be especially careful. Look at the A20 vulnerability. They didn't read the data sheet of Intel chips when they changed it. And look at the Visor. They didn't look at the Intel data sheets with a Visor workaround, and they, didn't also read the data sheets at all with the A20 thing, or else they would have had the idea, perhaps, even when reading just the index. Number 10, don't just read data sheets, also read standard literature. So if you're doing crypto, read at least the applied cryptography book. It seems like Microsoft hasn't done this. For all those who are constructing security systems in the future, now that we have Wikipedia, it is a very good hint to go on their page and look at all the references there. For example, that old 1996 paper that said that T was vulnerable is directly linked from the Wikipedia article today. So at least if you use Wikipedia today, this shouldn't happen anymore. RC4 is a hash. They didn't read Schneier, and T is a hash. They didn't read that paper. Mistake number 11, get experienced professionals. Your engineers must have a background on security systems. We know for a fact that Microsoft did not really have security experts, but they had those people who did the security system on the Xbox were those who did web TV before. Web TV was that set-top box system by Microsoft. It was an embedded system, it was home entertainment, but I don't think it had any security or any really strong crypto or anything. So they should really have hired some good people. And students on internships, I know that many of you may be students, and there are many brilliant students, but if I were Microsoft and I wanted to spend many billions of dollars on a new gaming console, I would really get well-paid professionals. We know of one person who did an internship and worked on the security system. He put it in his resume on his website. In the implementation of the secret ROM, it is obvious that this person that did it had no background in crypto. Mistake number 12, check that your code is complete and catches all the cases. If you don't, your work has the opposite effect. It gives hints to hackers. That has, you can see this with the secret ROM turn-off check, which had the compare there. And because they had the compare there, at the beginning we didn't know what this compare meant. Until we could finally try it out. But it gave us a big hint where to attack, and just change that and we had it. So it had really the opposite effect. And the same was true with the hash everything but the fonts. If everything is hashed but the fonts, we attack the fonts. If 100 megabytes of data files are not hashed, we would start possibly alphabetically. So this also gave us a hint and accelerated the whole development. Okay, 4 left. 13 leftovers. Mistake number 13. Look at the final product from the perspective of a hacker. You must really hack stump and disassemble your final builds from the perspective of a hacker, because they had that old version of the secret ROM in Flash that was so close. If they had been a bit more unlucky, they would have linked the current version of that. So the secret ROM wouldn't have been secret. That was really big bug. Number 14, do tests on your final system. Again, with the final components in place. Because small changes, as always in software engineering, small changes can break everything, everywhere else, and especially in security. And they did that in two things. One was when they switched from AMD to Intel. It broke everything, and when they switched from RC4, 5 to RC4, it also broke everything, and they didn't test again. And there are three more policy mistakes. Mistake number 15 is source code. Keep your source code safe. Okay, open source is a great thing, but with a security system, it might sometimes be a good idea to have security by obscurity, yes, in the source code. Because what you need is engineers you can trust so that it doesn't leak. The Xbox source code has leaked. It hasn't been used for Linux development or anything. It leaked quite late, so it hadn't such a big impact. But it would have accelerated everything a lot when it leaked later. The piracy people could easily compile their own kernels with their custom logos in there for their custom mod chips, or support bigger hard disk. All that could then just be easily done in source code. It's not so much about knowing how it works, but having the code and being able to compile it yourself and not hacking around. Number 16, speaking of source code and safety of source code. Although you should have your source code safe when designing a security system, you must have many people that look at the design and the implementation. It is not a good idea to prevent your people from seeing the source code. Instead, have many people look at it, but find engineers that you can trust. That has obviously happened on the Xbox because there was a very weak quality assurance on so many parts. It seems like so few people had a look at it, because when we had the ROM, only 3 or 4 people who read it at once saw the possible problems. So if Microsoft had 3 or 4 more good people, they would have seen all these problems. And the last mistake is do talk to hackers. Because your enemy, you must know your enemy. You're not on one side and on the other side that's the hacker, and you never communicate or anything. Microsoft thinks that they shouldn't talk to terrorists, but this is stupid because it sometimes really makes sense. Especially the Linux guys, we're not Microsoft's enemy by definition. Some people may be, but not necessarily. And they want to reach their goals. They don't want to break everything and make everything bad for Microsoft, but just reach their goals. And there are possible compromises. One possible compromise after all these hacks would have been, for example, that Microsoft would have allowed Linux to run if in exchange that possible vulnerability hadn't been disclosed. That would have been great for the Linux people because it would have run out of the box. You could have sold Linux for the Xbox on unmodified boxes for every home user. And on the other side, Microsoft wouldn't have had the piracy problem they have today. But they chose not to do it. They chose not to talk to hackers. They didn't talk about the 007 exploit. It was we had such a hard time reaching anyone. And about the font exploit, it was exactly the same. I'll leave you alone with the latest slide, the summary of the Xbox security system. I don't think there's so much to say at this point. And at this point, I'll hand over to Felix, who will have at least half an hour. There will be a break afterwards, so we can take more time. So we'll have at least half an hour for the 360 talk. Nein, das bin ich.
Ach so.
Oder? Das hier, nein.
Nee, dann ist da drüber.
Das hier?
Ja.
Ja. Yep.
Wie bediene ich das?
Rechts links.
Hello. Yeah, hello. I'm Felix Domke, and I'm going to tell you a bit about the. Please fix that.
Yeah.
Okay. That's still missing. No, okay. Yeah, I'm going to tell you about the new Xbox, the Xbox 360. It's just released, I think, a month ago here in Germany. So there isn't, Linux is not yet running, but okay. I will give you an overview about the hardware and so on and tell you about possible attacks. So a big fat warning first. Michael, kann man das irgendwie entfernen da? Okay. Some of the information I'm giving you are purely speculative. So we've got some information from pretty obscure sources, and we don't know really if they are correct, but they look so. And so, I'm just telling you what we know and what we think to know. And don't panic if it's not really, if it's a bit different. It's really a new topic for us, but we're doing our best. So, the new Xbox, I think most of you heard from it. It has a new CPU. In fact, everything is new, but the CPU is the biggest change. It's now a custom CPU. It's not off-the-shelf hardware. So they stopped using x86. So they started using PowerPC, and they're using a custom CPU from IBM, which is a PowerPC CPU manufactured by IBM. Its code name is Xenon, which also gave a code name for the whole console, which is called Xenon as well. It's a 3-core CPU and runs at 3.2 gigahertz, which sounds very fast. But please keep in mind that the CPU is stripped down, so that it doesn't support out-of-order processing of instructions. So usual code will really run slow on this if it's not optimized for this CPU. It will run, but it will run slowly. And because out-of-order execution is that instructions are reordered, so if a memory access, for example, is done, other instructions can already be executed, and still waiting for the memory access, which is slow usually, so waiting until it's done. But the Xbox CPU can't do this, so the compiler has to take care of reordering the instructions, so the impact is minimal. In order to optimize this further, they implemented 2 hardware threads per core, which is something like hyper-threading on on normal CPUs, Pentium 4. This isn't a good thing, but they had to do it to improve the performance. So they have a pretty fast CPU. Other features is a very fast a VMX 128 core, which is something like Altivec, but improved with 128 registers. They had to improve improve the architecture this way and implement new opcodes for handling the new register set. Normal Altivec only has, I think, 32 registers, I'm not sure. And the CPU has some cache and relatively large second level cache, which is shared by all the cores and is pretty fast and can be used as normal memory, which is quite common in consoles today. The CPU, many people ask me why Apple, for example, doesn't use the CPU in some computers for them. But the reason is simply that this is not really a general purpose CPU. It can execute normal PowerPC code, but it just does not perform. So it works quite well in a console because all the hardware is fixed and all the games are fixed, and you can optimize the compiler for exactly this CPU, but it just doesn't work in a normal computer or something. So this is not better than a G5, it's just a different thing. It's called PowerPC and it executes PowerPC code, but you just can't compare to a G5 or something. For ideal performance, you really have to have multiple threads running, and this is a problem because usual code is single-threaded, and most games are single-threaded, and application software is single-threaded as well. So you can only use a quarter of the performance if you use only a single thread, and game developers have to start using multiple threads for their games, which is pretty new. All other consoles only have one CPU core, and so it doesn't make any sense there. And it's really hard to get all the performance out of this chip, but we have to see. Yeah, it was told, I'm not sure if this is correct, that the current Xbox game mainly are single-threaded, so they use about a quarter of the performance or something. We have to see how this evolves, and maybe there's some approaches to make generic application software multi-threaded without much effort, but it's not so easy. So yeah, it's really not a replacement for a normal CPU. It's just, it's a custom CPU for a game console. The GPU, the graphic processor, is from ATI. The code name is Xenos. It's a pretty fast chip, I was told, but I don't know anything about graphic stuff, so I just believe them. They have embedded DRAM on the chip, which is pretty fast because they can have a very high clock rate to the chip and so on. They use it for the frame buffer. But that RAM is not on the same die as the GPU, but is on the same chip, so it's a multi-chip package. And it's kind of intelligent RAM, which can also do Z-compare and some 3D functions which are required. So it's a totally custom CPU as well. The GPU is also used as a north bridge, so the memory is connected there, the CPU is connected there, and the south bridge, which is connected using PCI Express, is also connected there. Then they have a DVD-ROM. It's pretty much the same like the old Xbox. This time they used a serial ATA connection, but everything else I think is mostly the same. They're using off-the-shelf hardware for this. They have a proprietary power connector and tray connector, but that's all. But the firmware is a bit different because it can do security functions. It can verify a DVD if it's a burnt one or if it's an original one. So this is pretty, should I say, it's pretty important that nobody can fake around this check, so it can run pirated CDs or something. But it's very hard to make off-the-shelf hardware secure, so they choose to pair drive firmware with consoles. So the console has a key and the drive has the same key, and if you exchange the drives, it won't work. And I think they wanted to prevent that somebody writes a firmware which doesn't really check it, but always tells the console that the game is okay, it's a real game disk. But you can't do this unless you always use the correct key fitting for the specific Xbox, which makes it pretty hard to sell something which requires reading out the old ROM and inserting a key and then flashing a new ROM and then soldering that in. So that's, I think, a trade-off between costs and security, and we already knew that this is no good. We have to see what happens. The peripherals like the controllers, are USB again, but this time they didn't use the proprietary connector, they used standard USB connectors. And there's even a driver in the Windows update for the Xbox controller, which is nice. There's a Wi-Fi adapter, which is USB 2, and there are memory cards. They have a proprietary connector, but are USB 2, as always. They have RF controllers. They are using something in the 2.4 gigahertz range, but it's something proprietary. It's not Bluetooth, it's not Wi-Fi, it's something else. But they seem to tunnel, in effect, some USB over that using proprietary protocol, simply to make it easier on the console side to handle the different controller types. And all the USB ports are high-speed USB, so if finally Linux will run on this, it will be nice that you can attach all your hardware. Until that, it's pretty useless. The hard disk, on the original Xbox, I think you all know that the hard drive was locked with a key, with the password. So each console had a different password, so you can't just take out a hard drive and put it into a PC and read and write to it. But as Michael already told us, this wasn't really successful because you could hot swap the disk, you can sniff the password out of it. So in effect, it just wasn't secure, so they dropped all that locking, and the the hard disk is optional, by the way, and you can just read it out using a PC. It's a serial ATA hard disk. And yeah, the hard disk, they have, the serial number of the hard disk is signed and stored on the hard disk, so they can check if this is the correct data for the correct hard disk. So if you buy some content, you can buy games in that Xbox Live marketplace or something, or you will be able to buy games. You just can't copy hard drive images, but you can take a hard drive to a different console and plug it there and then it works, but you can't copy the hard drive image to another hard drive with a different serial number. Yeah, it's, I think, simply for protection of the bought content. So on disk format is XTEF or FATX with swapped endianness. So I bet they just recompiled their code. The PowerPC CPU is big endianness. So yeah, the format is swapped, but everything else is exactly the same. Of course, security is an issue as well on the new Xbox. Why should it not? They have a couple of threads. Okay. So the first real big issue are wares or pirating users, which don't want to buy their games but play their games without paying. And Microsoft obviously has to provide a secure platform to make it, to make the game developers supporting their platform, because if they can't sell their games for a specific platform because they all get copyright, they don't want to support the platform. So the next thing is they don't want non-licensed code like third-party media players and so on available for this Xbox, because the hardware is much more expensive than it is sold. So they, I think they pay like $150 per box. So they don't want that you use the box for something else than playing games or using their software. Next thing is that they seem to want to push their proprietary technologies, so they want to push the Windows Media, their specific formats. They don't want MPEG-4, but their Windows Media. They don't want any Mozilla or something. They want their Internet Explorer when they have a browser and so on. So they really don't want you to execute your own code on it. And Linux, would be a pretty big bad picture if it runs on the Xbox again so fast, like it was happened on the first Xbox. So they will have to, or they implemented security against this. So unlicensed code should not be executed. If we look how this was defeated on the Xbox One, the wares people developed mod chips which replaced the original ROM and allowed the kernel to run executables from all media, so you can copy the games to the hard disk and run it from there. This was a kernel hack, and they sure want to prevent this again. Then mod chips also allowed you to execute completely unsigned code, which you just compiled using maybe a free tool chain or something. And finally, Linux was able to. Linux has to take over the control of the whole system. So games, as Michael told you, are executed in supervisor mode and not in a user mode. So Linux was able to completely overtake the system, because it was, when it was executed in a game context, it was executed in a supervisor context. Microsoft, they had to fix this, and they first had to think again of their chain of trust. Does it really work? Well, I think Michael showed you that it does not work, because first, there are games which can be exploited. There are many games, in fact. Then there could be evil game developers which implement something like a backdoor or something which doesn't get caught in the process when Microsoft is reviewing the binaries or the code. I don't know the process of this. So they could implement a backdoor which could break the security. And finally, the idea was that if, however, wrong code, which means unsigned code, non-original code, is executed on the system, it should not be able to take over the full control. This is not a new approach. I think every decent operating system is able to do this. You can execute code in their own context, and let it not overtake the system. But it's a problem if you have to push big amounts of data to the hardware, for example, the graphic data and the sound data. And it's not so easy to do this in a user mode. It might be possible, but it's not so easy, and it's a trade-off between speed and security again. So having a user mode is not really an option. And next, the kernel could have some exploits so you can have something like a local root exploit or something to get into the kernel mode, and then you had the full control. And the kernel is very complex because it would handle all the hardware access. So this was not really an option. And finally, if you're able to write to the memory, for example, by attaching some logic to a memory chip or something, you could set the user permissions maybe by toggling a single bit or something, which could be possible in hardware. So they had to do something else, which is the hypervisor. The hypervisor is nothing new. IBM used it on their server processors for a long time ago for virtualizing server machines, so you can run multiple operating system instances on one server. But on the Xbox 360, they used the hypervisor, and it's only used for security there. And the console has some secrets, mainly some keys, and the kernel still runs in supervisor mode, but communicates with the hypervisor. For example, if something needs to be signed or decrypted or encrypted or whatever, it calls the hypervisor. The disk authentication, for example, the first thing a mod chip has to hack in order to allow pirated copies to run works together with the hypervisor, so it's not so easy to patch. If you have full access over the kernel, you would still have to, you can't simply tell the kernel that the disk is authenticated because the hypervisor managed this. And the decryption keys for the executables on the DVDs are still kept in the hypervisor, so you can't just load a new binary manually from disk. However, as I said, for speed reason, hardware access is not done through this hypervisor, and the complexity of the hypervisor is really kept as simple as possible. So, in order, to make it more secure. If it's simpler code, it's more secure, obviously. The hypervisor, as said, contains some secret, which are keys, and should not be read from any memory. So if you attach some memory sniffing device, which is might be called a hero attack, because you have to sniff a really much number of wires, or you could do some local exploit or whatever to read the whole memory, or use hardware to busmaster from the memory. For example, you can tell the network chip to busmaster from the physical memory and send a packet out. You could dump the whole memory, as said, because the supervisor or the games have access to the hardware. It's not done in the hypervisor, it's done in the supervisor. So you could instruct the network card to send out an image of the physical memory. So they choose to implement encryption, and they added an encryption engine in the custom CPU, which allows certain memory regions to be encrypted. And they will be transparently decrypted on the fly when executed. So a game, for example, doesn't know that the memory is encrypted, but only if you look at the physical memory, you see that all code is encrypted, in fact. The hypervisor is encrypted too, and it's not transparently accessible from the user memory, only from the hypervisor memory, of course. And the user or kernel code uses syscalls. That's an exception on the PowerPC to communicate with the hypervisor. And all other interrupts, for example, by external hardware, are processed by the hypervisor as well, but chained to the kernel then. This is an example. This call, for example, it's a function to make some hash, I think, which includes some prefix or which is secret. So you can have to load the registers with the address of the pointer of what do you want to hash, and give it a place to store the result and so on. And the hypervisor doesn't use the MMU. It uses physical memory, so you have to convert all your pointers to physical memory. Yes. So Microsoft in fact learned something. They learned that high-speed buses can be sniffed. They are putting the encryption device in the CPU, or at last we think it's in the CPU, because everything else could be sniffed. They know that keys can be snuffed out with, if you have really expensive hardware, you could maybe even sniff inside the CPU and you could derive the secret key used for booting. And so they choose an approach. They give each Xbox a different key for booting. So each Xbox user has a completely other boot image because it's encrypted with another key. And IBM offers these e-fuses. Fuses are in the chip. They can be read in the chip and they can be burned. But normal fuses can be burned while the production with a laser device or something. And these e-fuses can be burned after production with a CPU instruction or something. So they are able to give each Xbox CPU a different key, which is very important because if somebody sniffs out a key of one Xbox, they can't produce a flash ROM which works on other Xboxes because each Xbox has a different key. That's a very strong, very strong security at the first look. IBM normally uses these e-fuses for parameters which differ from chip to chip, maybe due to production issues. So for example, the exact voltage a chip must be operating could be different from chip to chip, maybe some millivolts more or less or something. So they measured while production and set the e-fuses accordingly. But it could be perfectly used for having per CPU keys, but we don't know. It's still unconfirmed if the e-fuses in the CPU are actually used for security or not. There's a paper from IBM about the CPU and it doesn't mention security at all, but maybe they just hide it or it's just not implemented there, but for example in the Northbridge or something. Additional security, yes, non-executable pages is not really new, but I think it's new to consoles. In fact, the official linker, it was told to me from Microsoft, doesn't allow writable and executable segments. So they either have to be writable or executable, but not both. And if you do this and have your stacks non-executable, you can't do the traditional buffer overflows anymore. But as we all know, there are ways to work around this, but they are very hard if you don't know the exact code on the system. And the code is, of course, encrypted, and that makes it much more difficult to do a buffer overrun. Of course, if you have ideal software, you don't have any buffer overruns. But if there are any buffer overruns, they aren't as easy to exploit as previously. So yeah, we have to see if this works out, but they tried it at last. Possible attacks, there are no real attacks until now, but recently somebody dumped the kiosk disk, and there are Xboxes which, it's a kind of demo disk. So they offer information about the Xbox and so on, and have some game demos on it, and somebody dumped that disk, and well, each binary on the disk, which is executable, is of course signed, so you can't change anything with the private key, which isn't known, and the Xbox can check if there's nothing changed. But there's a bit field which says the allowed source media. For example, a normal game executable, of course, has said that it can be only run from an original Xbox game disk. But this kiosk disk, the binaries on that kiosk disk were signed as run from everywhere. So you can put them on a normal CD, you can burn them, and they run. That alone isn't really a security threat, but maybe the games are exploitable or something. Then it would become a security threat because you can just burn them to CD and then execute them. Data files are still not always signed. So this could be a way to attack one of the games, and if we find an exploit in one of these games, we would have a way, to run maybe our own code or something. There's still a new type of processor now, because the GPU does support shaders, and shaders are mainly for graphic processing, of course, but they are so powerful in the meantime now that they can be almost used as general purpose CPUs. Well, they can only, or are optimized for float numbers and so on, but they are code, and especially on the Xbox, they can read and write to physical memory. This is done for loading geometry data and so on. And they have a special instruction called a mem export, and they can access the physical memory. And now if some games, they have their shaders in non-signed areas, so we can change them and burn them on CD. And maybe it's possible to make a shader which can then attack the physical memory, write our code there and so on. But as I said before, all code is encrypted in physical memory. But obviously the data is not encrypted in physical memory because, for example, the GPU must access geometry data and textures and so on, and they can't be encrypted. So we could change data, we could change stack frames and so on, modify return addresses, and it could be pretty much fun messing around with shaders and their features to access the memory. This is one possible attack. It's a very recent discovery of this kiosk disk and the shaders which are there. So we have to see if this works out. Currently there is no real attack, as I said, but maybe, time will tell, and it's just a month since the release. I hope this changes. So, the current state is so far you can't run Linux, but the good thing is you can't run any pirate games, and that is good for Microsoft. And if you want to keep track with the information of the, there's a project called 360. The website is marked there, and Michael just want to show you something. And well, so maybe there are people who never saw an 360 before, so this is one of them. And this is, well, the upper one here is the mainboard of the 360, and the lower one is some hardware we have attached, trying to hack it or sniff it, but provide us a lot of information, but no real attack yet, but I hope this will change. That's, I think, all which can be told about the Xbox now. Just look at that page. It's all new discoveries will be posted there, and thank you very much for your time.